Okay, so I've introduced these concepts of how permeability and equilibrium potential are going to play into the determination of membrane potential in a neuron. Now let's take a look at what a typical neuron looks like when it's at rest. Okay, so at rest, a typical neuron has a bunch of channels around that are open all the time, and we call those leak channels. Okay, so this is just a diagram that shows a channel that's just always open. And ions are going to be able to move across it at any time. And that's what's going to determine the membrane potential at rest. At rest, we have about 40 times more potassium leak channels than we have sodium leak channels. Okay, and then I also just want to remind you that we have the sodium potassium pump at work setting up those ion concentration gradients. But let's take a closer look at the implications of this right here, the fact that we have so many more open potassium leak channels than sodium leak channels. So to further explore this question, I've made this table right here that shows you the permeability of the membrane to these various ions. And then I have this column here to remind you of their equilibrium potentials. I want you to take a look at these permeabilities, take a look at these equilibrium potentials, and using the principles that we have been covering in the past several slides, see if you can estimate what the membrane potential will be. So go ahead and hit pause, think about this for a while, see what you can come up with. Okay, so let's go over this. So we have a very high permeability to potassium. And this is, again, this is a typical neuron at rest. We have a very high permeability to potassium, which means that potassium is going to be able to move towards equilibrium. And in doing so, it's going to bring the membrane potential close to its equilibrium potential. Therefore, at rest, a neuron is going to have a membrane potential that's kind of close to the potassium equilibrium potential. However, we do have these other ions that come into play, and we have some permeability to these other ions. And as you can see, both sodium and chloride have equilibrium potentials that are higher than negative 90 millivolts. So as they move towards their equilibria in a limited way, they are going to end up pulling that membrane potential a little higher. Does that make sense? That's what I would usually say if I were doing this in person. So basically, as a result, we have a resting membrane potential that's close to negative 90 millivolts, but it's not quite that negative because sodium and chloride are pulling it up. Okay, so for most neurons, we have a resting membrane potential of negative 70 millivolts, which actually is the figure that you have been seeing all along in all of these slides, right? So this is a typical neuron at rest, and it's got its membrane potential at negative 70 millivolts. Okay, let's move on to another example just for practice. Okay, so let's pretend that we have these permeabilities for these ions right here. Let's also pretend that we have these equilibrium potentials for these ions right here. Okay, and I just want to emphasize these are atypical values. This is not what you would normally see in a neuron. You wouldn't normally see these permeabilities. You wouldn't normally see these equilibrium potentials. but just for the sake of applying the concepts, let's think through this. Okay, so here's your question. Can you guess, can you estimate what the membrane potential will be? And then here's a follow-up question. What if we changed the sodium permeability to 20? What would membrane potential look like in that case? So go ahead and hit pause, think through this, see if you can come up with some answers. Okay, so hopefully you were able to figure it out. We will be discussing it in class. Now it's time to move on. This slide is just here to remind me and to remind you that I will be giving you a link to this video here that it's a really nice animation that demonstrates resting membrane potential. I encourage you to watch it. It's very nice. And it also explains resting membrane potential in a slightly different way than I do. So it's helpful, you know, because this is kind of I think, kind of a difficult concept. So it's helpful to get different angles on it. I also encourage you to read about it in the book because I think that explanation is also slightly different. So, so you can kind of see how it's explained in different ways, and hopefully between the three of those sources, you can get a solid understanding of how membrane potential works. Okay, so that basically wraps up our discussion of resting membrane potential. Here are your learning goals right here. I'm not going to read them out. And then here is some vocabulary for you.